Thank you all for making this kind of early presentation. It's relatively early for me. So, as I'm trying to keep the old school way of crypto talks and not have any logos and project chilling, especially since I'm an independent developer and I in like 12 projects simultaneously, I cannot represent any. So I'm always trying to bring independent topics, which are usually personal driven ones. Okay. And this is also a personally driven motivation. So being an independent, I work in an independent contractor network. And usually when there is the misunderstanding with one of my partners that I'm an expert in tokenomics too, which I'm not, I always reached out to this expert economist friend of mine, a pair actually, a physicist who did the actual modeling and a young guy who always did the making up to date in the crypto market. And since I've lost them, I had to find a way as a developer, like a quantum researcher, without all the necessary knowledge in economics, that how do I make the tokenomics system works. And the only tool I had at my disposal is that I suppose I'm good in mathematics. So today's talk is formal methods and control theory on tokenomics design, and the advantage is how I hacked this. On the agenda, I'll formalize the problem that I saw, like lacking in tokenomics design generally, then like key components, most importantly the simulation technique, and I will list a couple methods in control theory that you can incorporate when you are making a new ERC20 tokens. And then at the very end, I'm gonna explain a little about that you're introducing a Stackelberg competition into your tokenomics and how do you solve that. So the problem I've seen with many of my partners is that most people did realize that making an ERC from scratch is engineering, but it's only like 20% IT engineering, programming engineering. Yeah, writing smart contracts is hard. Writing safe smart contracts is even harder, but in a product development term, it's only 20% of the work. The rest is mostly financial engineering and then product development. And people tend to forget this, that yeah, it's hard engineering and the financial engineering part is mostly missing. The methodology I've seen is that we're just gonna copy the best performing tokens from ICO drops because they did money. And they never realized that it doesn't fit your model here. You have to like do something special just for yourself. So heuristics and statistics won't work. Like even the total supply doesn't work like that. Most clients of mine selected the total supply for their tokens because it looked nice psychologically. It's like an even number and stuff. It shouldn't work like that. So one key component that's irrelevant of control theory and should be a key stuff in any kind of financial engineering is to use the Monte Carlo simulation methods. And I just listed a couple distributions you can sample from, your martingale from, when you are sampling the price that, okay, what price I'm gonna simulate on. According to latest research, crypto prices follow mostly normal inverse Gauss distributions, contrary to Forex and like common stocks, which follow mostly Gauss distribution, as crypto follows the Gauss bell curve, usually, but there are some times when it's like kicking in one direction a huge candle and then everything breaks. But normal inverse Gaussian can capture this very weird, highly volatile behavior. So you can sample your martingale with your Monte Carlo simulation, mostly using normal inverse Gauss. I brought some code example. By the way, the slides will be available as a website at the very end, and you can copy the codes. I may even edit and add some more examples at the very end. Here you can see that I just pulled from Binance the latest ETH USDT prices and just fit. I don't even know the correct parameters for the distribution I want to simulate. I just used scikit-learn fit, and it fits the Ethereum behavior in prices perfectly, and I can just generate 3 years of projections into the future with the assumption that it's gonna work the same as Ethereum market did. And also, since I saw the tendency this year's talk that you had to have AI in your talk, I also made it one with an autoencoder using PyTorch. You don't really need this, but if you have some super complex distribution, maybe a super low volume market with very low liquidity, they tend to behave weirdly, then you can capture it surely with an autoencoder in a couple lines. Next up is the example I told you that you shouldn't capture the total supply of your token based on psychology and statistics alone. This is also something that has been addressed way before. Actually, the first example I saw in regards to crypto is from Vitalik, from his blog. He modified the quantity theory of money to some crypto way. I personally like to use the Cambridge equation more, which basically says that the total supply of your token should be equal the holding period. This is the one that captures utility theory, which we are going to talk about, a super important part in financial engineering. So it should be the product of the average holding time of a person, of a wallet on the network, the price level in tokens, and the real aggregate value of transactions made. And if you did your homework in product design when you prior releasing your ERC20 token, PQ, so the price level and the aggregate value of transaction is visible in your market research because you did historical statistics that, hey, I'm covering this market, I'm tokenizing real estate, I don't know, average price in tokens that I want to release is P, and people purchase that much real estate the last 10 years, so PQ is known. You only have to figure out K, but in crypto markets, you just go to Etherscan, select a bunch of tokens. This you can do with statistics and heuristics, and you just check how often a wallet changes tokens. So K here is not volume, it's just how many times a single Ether changes hands. So for the following, for the actual control theory part, I'm going to use an example, the Treasury model, which was super popular since DeFi went to a rocket. And it's interesting because it also follows the burn-mint equilibrium model. So even if your token contract doesn't really burn or mint new tokens, introducing the Treasury model mathematically is the same because you're pulling or putting back tokens into public circulation. So it doesn't matter from the financial engineering aspect whether you burn the tokens actually or mint new ones or just pull into some Treasury because you are also present on a fiat market, which is mostly true. So most clients I work with are tokenizing something from the real world, from the fiat world, they say, and trying to reflect it in some kind of ERC20, which is hard because with this Treasury we have to play some kind of Stackelberg game and involve lots of oracles for that. And this game does have an equilibrium, of course, when you burn the exact amount of tokens you need to sustain your business and mint the exact amount that your economy needs, that your token economy needs, is fine. But it's not really realistic in an actual market scenario because you can't maintain the theoretical equilibrium like black swan events come, an FTX collapse come, and that's when startups really have to shine. Like you have to prove your adaptability to the real world market. And that's when control theory comes back. Like you have a trajectory you want to follow, which is the equilibrium in this model. And you have to, when you're diverting from that trajectory, you have to super quick go back to that. So we need something that captures utility theory, not just the formal game theory of the burn-mint equilibrium for our example. And it's super useful because utility theory is the part that captures subjectivity, like personal subjectivity, how much this token is worth to you. And it differs for every person. Like the more cookies you eat, the less satisfaction you get from the next cookie. And it's the same with money. Like $1,000 won't motivate a billionaire anymore. And it can be quantified mathematically, even though it's subjective. And when you do, you reach very interesting stability properties in your Monte Carlo simulation. The example here, and actually some techniques too, comes from a free ebook that I really recommend you can download from Stanford's website, Foundations of Reinforcement Learning with Applications in Finance. So the example, the Treasury example I described in words is formally this one. So the total supply of our token, let's say, varies or changes as I withdraw tokens from the circulation. So the tokens purchased back, this is TP in the formal model. So the tokens I purchase back, and I give back some, like the buyback, divided by the price, and I have to offer a premium for my network, otherwise they're just gonna dump the tokens on Uniswap. So I offer a premium here. So I'm the rational choice when it comes to how do I maintain equilibrium. So this is the example we're gonna use and stabilize in various forms of control theory. The example comes from actually the paper I listed here, which is kind of the motivating source, how I got into financial engineering and control theory in regards for tokenomics design. So method one, kind of the most naive one, is a linear quadratic regulator. Pros, it's time invariant. Anytime you are, it doesn't matter if it's your first year of your projection you want to stabilize or the third one, it's going to work the same. You only have to do the LQR matrix one, and every time something happens, you just run the same algorithm, like you just do the same matrix multiplication on your state, and it's going to be the most stable version achievable on your market currently. It's also super deterministic, which can be a problem too on financial markets because people are going to speculate on it. The biggest problem is that most DeFi logic, especially since CDPs and all became a trend, are not time invariant or linear anymore. And LQRs, the name suggests that you have a linear system of, you have a linear dynamic system, so your total supply, your price, your treasure sizes changes linearly, which is usually not true anymore, and your constraints are quadratic. So the formal problem is that we have the state x, and we have the control vectors, which are our purchase back and our premium, how much premium I gave or I want to give to the network to sufficiently motivate them, but still not lose too much. So this is what we want to optimize here. The code example looks like ugly, but this is everything you need here. So it's like 9 lies. You can optimize a treasury model. I used MIT's and Boston Dynamics open source library for robotics to optimize here. You see the X variables are my total supply, the USD pool, my token pool, and my price. And the control, where I have like the little sliders that I want to stabilize, is how much tokens I buy back, how much USD I buy back from tokens, and the premium I do. And I expected every year a 10% increase in my revenue model. And the result is a matrix that every time you do the multiplication, it just stabilizes you, like tells you exactly how much premium you have to offer to follow the 10% increase. This is still not a guarantee, but very useful and still better than heuristics. Here I calculated here I did a trick because, as I told, most DeFi models are not linear, so I just did the second order Taylor approximation at any point to make it look like it's linear, so the technique is still approachable, and the actual optimization part. Method 2, model predictive control. It's a little more evolved because now we can have a little uncertainty, which we do have a lot in crypto networks. So you can have like a range, a boundary that I don't know exactly how much tokens I want to have or where the price will go. Like let's have a worst case and the best case scenario, a boundary, and model predictive control can account for this within its own limits, of course. The problem with this is that it's just like with AI, it tends to underfit or like reach a local optimality that you can't really get it out from. And it's very slow to compute, and you have to compute it like every time you wanna account for a black swan event. So for this, I use the open source do MPC library. I have to step up with the code examples that are gonna be available. So yeah, it's the same equation that I started with the example, how the token pool or the total supply changes according to the Cambridge equation, the USD pool, and the only questionable part is here the SI0, which is my projection, so my demand, how much demand I projected for my actual product in the fiat world. Our constraints for the changes, and then I set up the controller using do MPC, the horizons. I want robustness, of course, that's my whole plan. Put into the parameters, start state, which is like the token generation event state, and just let's see what's the next control parameter has to be. PID, we are getting closer to real world because PID has been used in the wild. It is also the easiest to implement because PID is just a very engineering geeky way to express present, past, future. P is the part that how wrong are we right now with our tokenomics model compared to what we projected. The I part, the integral part, captures how long have been wrong about it, and the D part is how sensitive are we with the parameters. So if I try to change what direction and how much will I go, basically. Here is a very hardly seen visual representation of what I just told, like the three components, past, present, and future. The problem with PID is that tends to like overshoot, especially if you cancel one of the terms, which did happen in the wild there. So RAI stabilized its stablecoin price using a PID controller, or more like a P controller, because they did realize the biggest problem with it in DeFi and in Web3 is that the D part especially is prone to adversarial speculation. Because if it captures the sensitivity of your token, it can be used for trading, because if you know exactly how much premium you're gonna get with the treasure model in the next block, you don't have an arbitrage-free market anymore. So people have a deterministic way to speculate on your prices with here, and that's why RAI actually nulled out the D part. The last method I'm gonna cover is my favorite that is not contained in the original paper. I listed here, I just found it through experiment that this is the best, is Markov decision processes, which is kind of the hardest to implement. But the good part is that the output here is not a single point optimization in time. It's a whole policy you can give to your client. And as an independent, it's very nice because I don't have to maintain my tokenomics designs anymore. I give a ready policy and I just tell that, hey, follow this. Anytime something happens, you just rerun it and it will reach equilibrium. And it also has many open source libraries, and you don't need to deal with nasty ordinary differential equations, because those are hard, even though like Web3 is super closed optimally, your Web3 model. That's why you are going into smart contracts, because you realized that your business model is so contained, so market clearing and closed that it can be solved fully automatically with smart contracts, and usually those are hard to model with ordinary differential equations. So you can solve a Markov decision process using policy iteration, value iteration, kind of average case in Q-learning. The state-of-the-art methods to solve MDPs are deep Q network or proximal policy optimization. But I note here I found that when it gets to that you have to solve the tokenomics MDP using these two, it's likely your whole business model is faulty, so you just reiterate. It shouldn't be that hard on a Web3 CDP model or the Treasury model. It never should reach the complexity where you have to reach equilibrium with the MDP using deep Q learning. So here I actually asked ChatGPT to write me a value iteration solution, and I put in my normal inverse Gauss distribution from the Ethereum example as a start state, and asked the forward value iteration to give me the optimal policy. The problems with all of them, as I stated, is that everyone can solve this problem because all the data is public on-chain. The algorithm I just gave you away freely, and everyone can run it, so everyone can speculate on your price because everyone knows what's the next equilibrium is gonna be. Or more formally, we have a leader-follower game that thankfully has been formulated. It's called the Stackelberg game. So the rules are not symmetric anymore like in chess, because there is a leader and there is a follower, not the same amount of power for the game. And thankfully, it has an equilibrium that's slightly skewed towards the leader in terms of like staying idle. So you can solve this kind of Stackelberg games, like you have the optimization algorithm, your clients and your market will have, the buyers will also have the same. But since you are the controller here, you can force the other party into equilibrium at any time because you move first every time. They can see the rules, they can see what moves you made in the game because it's on-chain, on Etherscan. But still, with this knowledge, you can force them into the equilibrium. So conclusion, because I ran out of time. Use iterated LQR, oh, there is a typo there, iterated LQR when your models are easy. Most of the time they are. If you can't linearize your tokenomics for whatever reason, the first to go for is model predictive control. And if you have even more uncertainty, you are absolutely not sure about one dimension you are moving on, then use Markov decision processes. And whichever one you used, like techniques, always solve the resulting Stackelberg game because your speculators are going to solve the same game. So use the Klaus-Kuhl-Tucker conditions to solve your Stackelberg game here, and also publish that in your white paper that, hey, we used ILQR or NPC to solve our tokenomics model, because first, it's great marketing that you're not doing heuristics and statistics, that you actually had some financial model there, and because you're not going to be able to hide the moves you make, it's better to tell them ahead that here is our policy, please follow us, because then it's a win-win situation, even though it's a zero-sum game. And of course, this all relies on that you have a stable projection. So it's not magic, like it won't mathematically prove that you are stable in any kind of market environment. It just follows the trajectory, and you have to have a very sound business projection for your upcoming like quarters and stuff, because that's all I presented here is useful. So as I said, the slides are available online. I may edit or add some new examples here, and the code is copyable here, and here are my contacts where you can reach me with questions or outside. Thank you for your attention.